Picture this moment. Every star you can currently see in the night sky has already burned out. The sun is gone. Earth is gone. The word human means nothing to anyone because there is no one left to remember it. And somewhere in that darkness, drifting silently through a galaxy that no longer looks anything like the one we know, a small object built by hand on a factory floor in California is still moving. Not broken, not destroyed, just moving. That object is Voyager 1. And this is not a story about what it has already done. This is a story about what happens to it next. 10,000 years from now, 10 million years from now, 10 trillion years from now. Because unlike almost everything else our species has ever built, this machine does not have an expiration date measured in decades. It has one measured on a timescale that makes the entire history of civilization look like a single heartbeat. By the end of this video, you will understand exactly where Voyager 1 is going, what will happen to it along the way, and why the number 10 trillion is not an exaggeration. It is closer to an understatement. To really appreciate what is being described here, it helps to remember exactly what Voyager 1 physically is. It is not some sleek, futuristic probe imagined for a film. It is a spacecraft roughly the size of a small car, built using engineering and computing technology from the middle of the 1970s, carrying an onboard computer with less processing capability than a basic modern calculator. It launched on September 5th, 1977, atop a Titan Centaur rocket from Kennedy Space Center in Florida, just weeks after its twin, Voyager 2, had already been sent on its own separate path. The mission's original goal was modest by comparison to everything that eventually happened. Engineers hoped to get a close look at Jupiter and Saturn, take some photographs, gather some measurements, and consider the mission a success if the spacecraft lasted somewhere between 4 and 5 years before its systems finally failed or its signal grew too faint to detect. Nobody planning that mission in the 1970s was thinking about trillions of years or even thousands. They were thinking about getting usable data back from 2 gas giant planets before the equipment gave out. Right now, Voyager 1 is a little over 15 billion miles from Earth, moving through interstellar space at roughly 38,000 miles per hour. It has no engine running, no fuel being burned, nothing propelling it forward except the momentum it picked up from a handful of gravity assists near Jupiter and Saturn back in 1979 and 1980. That single detail matters more than it sounds. Voyager 1 is not flying, it is falling, coasting along a fixed trajectory with nothing left to change its course. There is no asteroid belt out here to dodge, no atmosphere to slow it down, no gravity nearby strong enough to bend its path in any meaningful way. Whatever direction it happens to be pointed right now is, for all practical purposes, the direction it will keep moving for longer than our species has existed, multiplied many times over. It helps to understand exactly how Voyager 1 reached the speed it currently carries, since it never had an engine powerful enough to achieve that velocity on its own. Mission planners used a technique called a gravity assist, timing the spacecraft's path so that it passed close by Jupiter and then Saturn, borrowing a small amount of each planet's own orbital momentum during the flyby and converting that borrowed momentum into additional speed for the spacecraft itself. It is similar to catching a moving train for a few seconds and then leaping off again, coming away considerably faster than you started, without the train itself losing any noticeable speed in the process. That rare alignment of Jupiter and Saturn, one that only occurs roughly once every 176 years, is part of why the mission was scheduled precisely when it was. Once those 2 assists were complete, Voyager 1 had already been pushed up to essentially its final cruising speed, the same speed, roughly unchanged, that it still carries today and will carry for the rest of its unimaginably long journey. Its power supply is fading. Voyager 1 runs on 3 radioisotope thermoelectric generators, devices that convert the heat released by slowly decaying plutonium into usable electricity. That plutonium is decaying on a fixed, predictable schedule, and sometime in the early 2030s, the last functioning instrument aboard the spacecraft will fall silent for good. But here is the detail almost nobody stops to think about. The silence of Voyager 1's radio does not mean the end of Voyager 1's journey. It only means the end of us listening. The spacecraft itself does not stop moving when the power runs out. It has nowhere it needs to be, nothing waiting for it, and nothing capable of making it late. Losing power simply means we lose the ability to hear from it. Its physical journey through space continues completely unaffected. It helps to understand exactly why Voyager 1 cannot simply drift to a stop the way objects do here on Earth. On our planet, everything that moves eventually slows down because of friction, air resistance, or the pull of the ground beneath it. None of those forces exist out in interstellar space. There's no air to push against, no surface to create friction, and the distances between stars are so enormous that gravitational tugs from anything nearby are far too weak to meaningfully alter its course. Once an object reaches the kind of speed Voyager 1 achieved through its early gravity assists, there is essentially nothing left in the emptiness of interstellar space capable of stopping it, slowing it, or meaningfully redirecting it. It will simply keep going in a straight line, indefinitely, the same way a ball thrown in the vacuum of space would never lose momentum unless it physically struck something. It is worth remembering that Voyager 1 does not make this journey alone, even if it will spend essentially all of it in total isolation from everything else humanity has ever built. Its twin, Voyager 2, launched just weeks earlier and took a different route through the solar system, eventually visiting Uranus and Neptune before also crossing into interstellar space of its own, several years after Voyager 1 made that same crossing. The two spacecraft are now heading in noticeably different directions, drifting apart from each other permanently, each carrying its own copy of the Golden Record, each destined for its own separate multi-trillion-year journey through a universe that will look less and less familiar with every passing epoch. They will never again come close to one another. Two identical messages in two different bottles, cast into the same dark ocean but drifting toward entirely different, unknowable shores. The first real milestone in Voyager 1's future does not arrive for a very long time by human standards, but on a cosmic clock, it is almost nothing at all. In roughly 40,000 years, Voyager 1 will drift within about 1.6 light years of a faint red dwarf star currently cataloged as Gliese 445, sitting quietly in the constellation Camelopardalis. To be clear, this is not a close encounter in any dramatic sense. It is not a flyby the way Voyager once swept past Jupiter or Saturn. 1.6 light years is still an almost incomprehensibly vast gap. Voyager will not be pulled meaningfully off its existing path by that star's gravity. It will simply pass by at a distance, the way a stranger might walk past a house standing on the far side of an enormous open field. Never close enough to be noticed, never close enough to matter to whatever might be living there. No planet orbiting that star, if any planets exist there at all, will ever register that anything passed by. By the time that quiet, uneventful passage occurs, every language currently spoken on Earth will almost certainly be extinct, replaced by others we cannot predict, the way Latin gave way to entirely different tongues over a much smaller stretch of time. Every current nation, every border drawn on a map, every monument built to commemorate a person or an event will be gone, forgotten, or transformed beyond recognition. Entire civilizations could rise and fall multiple times over in that same span. And Voyager 1, having just quietly passed a distant dim star nobody on Earth today has ever heard of, will have barely begun its journey. Skip ahead much further now, to roughly 5 billion years from today. This is the point at which our own solar system stops existing in any form we would currently recognize. The sun, having exhausted the hydrogen fuel burning in its core, begins swelling into what astronomers call a red giant. Its outer layers expand dramatically outward, very likely consuming Mercury and Venus entirely, and quite possibly reaching close, enough to scorch or engulf whatever remains of Earth by that point. Everything familiar about our particular corner of the galaxy, the blue oceans of Earth, the ring circling Saturn, the storm swirling on Jupiter that has raged for centuries, will cease to exist in any recognizable form. The solar system that built Voyager 1 will, in a very real sense, no longer exist. Voyager 1, by that point, will already be unimaginably far away, deep in interstellar space, completely unaffected by any of it. It will, in a very real sense, outlive the very star whose sunlight its cameras once used to photograph the swirling clouds of Jupiter and the icy rings of Saturn. The machine will still be out there, intact, cold, dark, and silent, drifting onward while the world that built it and the star that made that world possible are both gone. Around this same general era, on a timescale of roughly 4 to 5 billion years, an even larger event is already scheduled to unfold. The Milky Way, our home galaxy, is on a slow collision course with its neighbor, the Andromeda Galaxy. Individual stars will rarely collide directly during that merger, since the space between them is simply too vast for that to happen often. But the overall shape and structure of the galaxy Voyager currently calls home will be permanently reorganized, its arms and clusters rearranged by the gravitational chaos of two galaxies gradually becoming one. Voyager 1 will still be somewhere inside that newly merged structure, an anonymous, silent drifting point lost among the wreckage and reshaping of two entire galaxies fusing together. Bolted to Voyager 1's frame is something that carries its own separate clock, ticking down on an entirely different timescale. The Golden Record is a gold-plated copper disc holding recorded sounds, photographs, diagrams, and greetings spoken in dozens of languages, assembled under the direction of astronomer Carl Sagan and his collaborators, meant to describe life on Earth to whoever or whatever might one day find it. The record contains greetings recorded in 55 different human languages, ranging from widely spoken languages to some that were already fading out of common use even in 1977. It carries natural sounds recorded on Earth, including wind, rain, ocean waves, and the calls of various animals. It carries roughly 90 minutes of music selected from cultures spanning the globe. along with more than 100 images, encoded onto the disk, depicting everything from human anatomy to the structure of DNA to photographs of everyday life on the planet that built it. It also carries a diagram intended to explain how to actually play the record, along with a map showing the position of our sun relative to a set of well-known pulsars, an attempt to communicate our location in the galaxy to anyone capable of interpreting the diagram correctly. Gold does not rust. Copper, when properly protected from atmosphere and moisture the way it is out in the vacuum of space, does not corrode the way it would sitting exposed here on Earth. Scientists who have studied the specific materials used in the record estimate that it could remain physically readable for a period measured in the hundreds of millions of years, possibly stretching into the low billions, limited mainly by slow, random erosion caused by cosmic dust and radiation, striking its surface over such enormous stretches of time. That means the golden record will likely outlast the readable grooves of nearly every recording humanity has ever produced here on Earth. It will outlast every hard drive ever manufactured, every physical archive, every library built to preserve human knowledge, all of which face far harsher conditions here on our own planet, exposed to weather, corrosion, and the simple passage of geological time. Long after the very last hard copy of a photograph or written page has crumbled into dust somewhere on Earth's surface, this small disk, riding along on a dead spacecraft drifting silently through the dark, could still be fully intact, still carrying the recorded sound of a human voice through a universe that by then may no longer contain a single human being left to hear it. Now we reach the number sitting at the center of this entire story, and it deserves real context, because 10 trillion years is not simply a large number chosen for shock value. Astronomers who study the extremely long-term future of the universe divide its history into distinct eras. Right now, we live inside what is called the stelliferous era, the age during which stars are actively forming, burning, and eventually dying, replenishing the galaxy with new generations of stars as older ones fade. Current models suggest this era will continue for up to roughly 100 trillion years before the very last stars anywhere finally burn out for good, exhausting whatever fuel remains available for new star formation throughout the universe. 10 trillion years from now places us deep inside the final stretch of that era, though still well before its true end. Most stars similar to our own sun will already be long dead by that point, their fuel exhausted many trillions of years earlier. Only the smallest, slowest burning red dwarf stars, the most fuel-efficient stars known to exist, will still be flickering faintly, sipping the last remaining traces of their fuel across timescales that are almost impossible for the human mind to properly hold on to. Beyond the stelliferous era, astronomers describe an even longer stretch known as the degenerate era, a period lasting from roughly 100 trillion years out to somewhere around 10 to the 40th power years, during which the universe contains no actively burning stars at all, only the cooling, dead remnants left behind, such as white dwarfs, neutron stars, and black holes drifting through an increasingly dark and empty cosmos. 10 trillion years places Voyager 1 comfortably before that stage even begins. Still technically within an era where at least a handful of dim, ancient stars continue to shine somewhere in the galaxy it now calls home. The Milky Way and Andromeda merged long ago into a single galaxy, sometimes nicknamed Milkomeda by astronomers, will have long since settled into whatever new shape that collision produced, its stars rearranged into an entirely different structure than either original galaxy once had. And Voyager 1, or whatever fragments of it, happened to remain by then, since micrometeorite impacts and cosmic radiation will have slowly worn away portions of its structure across such an immense span of time, will still be traveling. Not toward anything in particular, not away from anything in particular either, at least not anymore, simply continuing along the same straight line it has followed ever. Since a rocket lifted it off a launch pad in Florida back in September of 1977, a trajectory now stretched across a length of time so vast that the phrase 10 trillion years becomes far easier to write down on paper than it is to genuinely comprehend. There is no guarantee that any star or planet will ever intercept it along that path. Space, even across such staggering timescales, remains overwhelmingly empty, and the odds of a direct collision with anything, even stretched out over trillions of years, remain extremely small. The most likely outcome is not destruction of any kind. It is simply indefinite continuation, a small, quiet, manufactured object drifting first through one galaxy, then through a newly merged galaxy, then eventually through a universe that grows steadily darker, colder, and more sparsely populated with each passing epoch, for a length of time that dwarfs the current age of the entire universe several hundred times over. It is worth pausing on just how young the universe currently is compared to the timescale being described here. The universe itself is currently a little under 14 billion years old. 10 trillion years is more than 700 times that current age. To put it another way, If the entire history of the universe, up to this exact moment, were compressed into a single day, 10 trillion. Years from now would fall somewhere roughly 2 years further down that same calendar, an almost absurd stretch of additional time compared to everything that has happened so far. And through all of that additional time, largely unchanged and untouched, a small spacecraft built by human hands in the 20th century is expected to simply keep going. We built something that was only ever expected to function for about 5 years. Instead, it may still be physically intact enough to matter long after every star currently visible in tonight's sky has faded into darkness. Not because anyone specifically engineered it to survive that long. Nobody working on the project back in 1977 was thinking in terms of trillions of years. It survives for that unimaginable length of time, simply because empty space, it turns out, is remarkably gentle to the small, solid things it happens to carry, as long as nothing large enough ever gets directly in their way. There is no wind to erode it, no rain to rust it, no ground to eventually swallow it. There is only the occasional, extraordinarily rare collision risk, and an overwhelming amount of empty distance separating it from anything capable of causing one. There is something quietly humbling about a species capable of building something that outlasts its own planet without even trying to. Nobody at Kennedy Space Center in 1977 signed off on a design specification requiring 10 trillion years of operational integrity. No engineer ran a stress test simulating the heat death of nearby stars or the merger of galaxies. The 5-year mission plan was written on paper by people solving a much smaller, much more immediate problem: how to get useful. Photographs of 2 distant planets before the equipment inevitably failed. And yet, almost by accident, in solving that comparatively small problem, those engineers built an object that may end up being the single most durable and long-lasting physical creation our entire species will ever produce, quietly outlasting every pyramid, every monument, every recorded word, and eventually every star that any human eye has ever looked up and named. Somewhere, out past the reach of anything we will ever manage to see again, even with our most powerful future instruments, a machine roughly the size of a small car is going to keep moving long after the sun that helped build it, the planet that launched it, and the species that dreamed it into existence have all quietly become history, remembered by no one, because there will be no one left to remember anything at all. That is Voyager 1's final destination, not a place marked on any map or chart. A length of time so long that the word forever starts to feel, by comparison, like the far more modest and far more achievable option.